All right. All right. Last one. The last stream. Already? Yeah. Already. Last live session, nuclear chem. Alright, so nuclear is like literally what we just did. Literally. That being said, though it's the most recent unit, and yes, it's hopefully fresh in your brains, it's not heavily tested, but has more questions on it than you would think. So, because of that, it's good to keep this stuff in mind. But anyway, at its core, nuclear chem is all about transmutations. Nuclear chemistry is literally the chemistry of the nucleus of the atom. You're changing the nucleus. So a transmutation is all about changing atoms, which is much different than what you've been seeing. A physical change is all about phase changes, melting, boiling, freezing, condensation, sublimation. Those are all physical changes. A chemical change changes the substance, but the atoms stay the same. So what does that mean? So that's like taking a hydrogen atom and an oxygen atom and making water. The atoms stay the same. We have H's, we have O's. But we have taken those atoms and changed them into a new substance. A nuclear change, or a transmutation, is when you literally change the atom. So, carbon-14 will release a beta particle and turn into nitrogen. So we have completely changed the atom. Totally new atom. And there's two different types of transmutations. Natural transmutations, which is everything on table O/N. They are unstable, and they are spontaneous, meaning they occur without any outside influence. Hence why they're natural. So everything on table O/N is involved in natural transmutations. Everything on table N, if you look at table N, all of their transmutations are given, and so are their half-lives. So gold here decays every 2.7 days and releases a beta particle. Carbons, every 5,700 years, releases a beta particle. Calciums, every 182 milliseconds, releases a positron particle. And you don't need to memorize these decay modes. They're all listed on table O, where the top number is the mass and the bottom number is the charge. So we have an alpha particle, we have a beta particle, we have gamma rays, which is no mass, no charge. We have a neutron, proton, and a positron. And all their symbols and what they mean. So you don't have to memorize the symbols either. They're all defined for you right there. So, the biggest way to tell if it's natural, though, is it has one reactant. So I'm going to do an example of every single natural radiation that you would see on a test. First one is alpha. So let's pick something from table N that has alpha decay. Go back. There you go. So, table N, alpha decay. Let's do radium 226. So radium's atomic number, because I don't remember, is 88. So radium 226, when it breaks down, so 226, 88, radium. Why am I writing the whole name? Mr. G, you goober. Will release an alpha particle. So that's what I mean by spontaneous, unstable, one reactant, natural reaction. There is only one reactant. It's not being added to anything. Radium here is going to break down and release this alpha particle naturally every however long its half-life is. And you need now to balance the charges and the mass. So if this side is 220, everything on this side must also add up to 226. So 4 plus 222 is 226. Since this side's 88, everything over here must also add up to 88. So 86 plus 2 is 88. Now, don't write X here. Don't write X. Look up whose atomic number is 86. And 86 should be radon. So write the symbol for radon, not X. Do not write X. And make that a lowercase n. Mr. G, you gooberhead. Okay, so that's an alpha decay. A beta decay, such as carbon-14, releases a beta particle, which has no mass and a charge of -1. So again, we need to make sure this is 14 on both sides. So 14 plus 0 is 14. That's easy. And then what minus 1 will give you 6? So keep in mind, these are two different sides of a reaction. If we have 6 over here, 7 minus 1 is also 6. And then we put the atomic symbol for 7, which is nitrogen. The only other natural reaction that results in a change of the atom is positron. An example of that would be, let's do calcium-37 here. So, calcium-37, when it decays, releases a positron. 37 goes in, 37 better pop out, 37 plus 0 is 37. 20 goes in, got a +1 here. What plus 1, excuse me, is 20. 19 plus 1 is 20. Put the atomic symbol for 19. We have potassium, which is K. Gamma is also natural radiation, but since gamma has no mass and no charge, we don't really see too many reactions in terms of balancing gamma, because it would just stay the same. However, gamma is the most dangerous. So if we were to organize these from least to most penetrating power, I'm just going to write penetrating power. It goes in alphabetical order. Alpha, beta is in the middle, and then gamma is the most dangerous. All right, alpha, beta, gamma. Least to most penetrating power. That covers so much of nuclear already. Half-life. Let's talk about half-life. How I usually set up half-life problems is just by making a quick little chart. Not even a chart, just like a flow. I don't know what to call this. But you always start with 100% of your substance, which is also equivalent to 1/1. In every certain amount of time, one half-life occurs, and you go down to 50% and 1 over 2. And then more time goes by. Half-life number 2, 25% and a quarter. And you just keep following this down until you get to wherever you need to get to. Meaning, it tells you a certain amount of time goes by, how much is remaining, you have this much at the end, what did you start with, how many half-lives went by if you have 1/8 of your substance, etc., etc. So, let's take carbon-14 for example. Its half-life is 5,715 years. So every 5,715 years, carbon-14 divides by 2. So, let's say it was what fraction of carbon-14 remains after, I don't know, let's say, let me pick a quick number, 22,860 years. So, it wants a fraction. So I'm going to start with 1 over 1. And I know after about 5,700 years, one half-life has occurred, and now I'm at a half. That's not 22,000. So, after another 5,700 years, it divides by 2 again. So now we're at 11,430, because I added 5715 to that. So this is 5715. I don't know why I rounded down. This is 5715. So after another 5715 years, a second half-life has occurred, and we're down to a quarter. After another 5715, we're now at this many years have gone by. A third half-life occurs, and we're at an eighth. After another 5715, we're at 22,860. Which means after 4 half-lives, we have a 16th remaining. So in 22,860 years, 4 half-lives have occurred, which means we have 1/16 of the original substance remaining. Let's say it said like, how many grams remain if a 200-gram sample of carbon-14 experienced 3 half-lives. So, you got to take that 200 and you just divide it by 2 once, twice, 3 times. 25 grams remains after 3 half-lives. And there's a bunch of problems like that where the strategy is pretty much the same thing each time. Make this chart, work forwards or backwards depending on where the problem is telling you to go. But either way, you're just adding, dividing by 2 for each step. Okay, there's artificial transmutations. So these are still unstable. They create tons of energy. Usually we're talking about fission and fusion here. So we're really cranking out the energy. The ones you'll see, like I said, are fission and fusion. And the easiest way to tell that you have artificial, even generically speaking, even if it's not fission or fusion, the easiest way to tell that you have artificial is if you have two reactants. These are typically not spontaneous, though, yeah. But usually you'll just see this as fission or fusion. Doesn't have to be. You can have a two-reactant reaction that's not fission or fusion, but usually they're fission or fusion. Fission first. Fission is division. What does that mean, fission is division? That means when you see a fission reaction, that heavy, large nucleus of uranium is going to split into many different smaller elements. And I forget what uranium splits up into, but we'll make stuff up. It's going to split into smaller elements. An X of 30 that weighs 100, and a Y that's 62 and weighs 133. Something like that. You get the idea. When you have fission, you have two reactants, and that one big reactant is dividing, fission is division, into smaller atoms in the products. Fission helps create a lot of energy, obviously. That's why we use it, but it can lead to waste issues. So you got to be careful. Remember, you're making these radioactive products. These radioactive products can have long half-lives. So where do you store them? What do you do with them? How do you get rid of them? That's the main issues with some of these nuclear reactions we got going on here. Fusion, I don't have anything good that rhymes here, is combining. So fission is division, fusion is combine. Usually you'll see this with hydrogen atoms. So those lighter hydrogen atoms will fuse together to make a heavier helium atom. And usually there's neutrons involved in here somewhere. But the point being is that fusion and fission have two reactants, two items on the left-hand side of the arrow. And fission is division, fusion is combining. Either way, what they're both really good at is taking some mass and getting a lot of energy out of it. Nuclear creates more energy than any chemical reaction. So, I've seen a question before that's like, compare the energy released by a fission reaction versus the energy released by a fusion reaction. Or not fusion, a chemical reaction. Or the one that was on one of my tests was, compare the energy released by a fission reaction to the energy released by a combustion reaction. And fission is going to win every time. Fission reactions were occurring in the big atom bombs that we dropped back in World War II. And last I checked, that was releasing a whole lot of energy. Like a lot. So, they both take some mass and convert it to energy. Fusion can create a lot of energy, but at the moment we don't use it as much because it costs more energy than the energy it outputs. Because it takes a whole lot of energy to fuse together those positive nuclei that prefer not to fuse together. The only other thing I can really think of is application of nuclear. So what application for these? And I see the same for reactants or radioactive elements pop up all the time. So we got carbon-14. That dates life. That dates organic matter. So it tells you how old former living things were. How old's this fossil? How old's this tree? Carbon-14 helps date life. Iodine 131 is for thyroid disorders. I for thigh. So just have that like pairing in your head. I for thigh. Cobalt 60 is for cancer treatment. Co for can. And then uranium, I believe it's 238. The number right now, I just did something with 232, so it's like in my head. Yeah, 238. Just want to make sure I did the right one. Uranium 238 is for like geology. So it like helps date rocks and stuff. Dates things that were never alive. Dates inorganic matter. Trying to piggyback to remember what was just on my nuclear quest, but I'm pretty sure that was really it. I can't think of anything else. A lot of it is like filling in the blanks with these reactions up here, with these natural decay reactions. Like if it releases a beta particle, what's this atom? Knowing that all these reactions are natural, being to say that they're natural, being to say that they're spontaneous. Knowing the definition of transmutation, which again is just changing atoms. One atom changes into a whole new atom. A carbon changes into a nitrogen, which is different. We've never seen something like that before. In your class, I should say. We've obviously seen this in the real world. But in your classroom, most of the reactions you do are chemical or physical, where the atoms don't change. Either their phases do, or the substance is formed is new, but has the same atoms. But yeah, just knowing natural, table O and N, unstable, spontaneous, all of these have one reactant. One reactant. One reactant. Gamma is the most dangerous, highest penetrating power. So in reverse order, it goes from least to most powerful, it goes in alphabetical order. Alpha, beta, gamma. Half-life, just set up this little like flow chart here. You always start with the full amount. Just keep dividing by 2. Keep adding the times together. Keep counting up the half-lives. I'll put a lot of problems on this on the review, because I think it's the trickiest part. Artificial, also unstable, still creates a lot of energy. Think fission and fusion. Both have 2 reactants. That's what makes it artificial. When you have 2 reactants turning into 2 new atoms, 2 or more new atoms, really, we have an artificial reaction. Fission is division. Take a big atom and split it. Fusion combines. Take smaller, lighter nuclei and bring them together. They both create energy from a lot of mass. So a whole lot of mass goes into a whole lot of energy. And then these applications. And that's about it. So, thanks for tuning in. Good luck on all your Regents you got next week. I'm going to put a bunch of practice problems on my teacher site. I'm also going to put a bunch of practice problems on Castle Learning for you guys. You know, we got to do a little bit of work at home to make sure we're successful in chem. Take care.